this just to I want you to stare at something that is rather remarkably difficult, surprisingly difficult, actually. With respect to friction, and that is this. So let's see, let's make up a scenario here. This is one of the classic examples and conundrums, actually, with respect to friction. I'm going to try to draw this reasonably to scale. So you have a ladder leaning against a wall, and let's see, proportionally, I'll say this is 4 feet. How's it going? We'll say this ladder is installed such that the distance here is 9 feet and the distance there is 4 feet. And interestingly, you probably can picture this. I didn't bring anything with me, but you can probably appreciate if you just laid an empty ladder against a wall like that, like it's not going to stay there. It's going to want to slide down the wall. Obviously, this end's going to go this way and that end's going to go that way, and this thing's going to slide down even with no weight on it or anything. But I want to look at the forces involved here and see if you can kind of make sense of this. So here's my experience of this. I mentioned this a little bit to you guys the other day, but I had in my garage, I had a ladder that did not have rubber feet on the bottom of it. It just was an aluminum ladder. So it was aluminum against a pretty smoothly troweled garage floor. So you can appreciate that doesn't feel very sticky, right? So rubber feet is a good invention for ladders. And so this just happened to be a half ladder, but it was like I wasn't climbing very high. I think it was about actually this scenario, I wasn't thinking about that when I drew this, but roughly I was barely climbing. I was only climbing up just a little bit. And so I get on this ladder and I step here and everything's good. And I step here and everything's good. And I step here and everything's good. And then I get up to here and then the ladder goes and slides out and I got all cut up and bloody and it was awesome. So there's a number of things about this that I don't know, I guess I want to bother you or want to, like, why didn't it fall earlier? Like, why did it fall later? And then why did it even fall at all? Because with respect to the kind of the free body diagram, the ladder, and we might decide to include this in a little bit, but for now, let's leave it off. But if I weighed 200 pounds, the weight of the ladder would be rather insignificant. Now it's not entirely insignificant, but if the ladder weighed 10 pounds, so we won't include this just to keep it simple, but you know, if the center of mass of the ladder was here, then me getting on the ladder in that position at 200 pounds and the ladder itself at 10 pounds being right there, like, isn't that the only forces here? Like, they're straight down. Why would there be any inclination for the ladder to fall? What are your thoughts? Go ahead, Caesar.
Because your distance, as you move up, your distance in the X direction is getting smaller, but your distance in the Y direction is getting bigger. And your force in your X direction is applied in your Y distance, and your force in your Y is applied in your X distance.
So again, to keep it simple, we're just going to pretend that, dang it. Gotcha. There's a part of me that wants to say, kind of based on the free body diagram idea, that, well, since that's, you know, that's against the ground, like, isn't that the fix right there? That's the equilibrium. So the ladder's on a concrete floor, so it's not going to sink into the concrete. Although you can appreciate if it was in the dirt, it's going to sink into the dirt some, right? But assuming I put this on the concrete floor, it's like mission accomplished. We're done. Some of the forces in Y are equal because the ground is capable of pushing back at 200 pounds. And so it shouldn't even matter where I am on the ladder. I go up and down the ladder, everything stays static. It doesn't really make any difference. But as I mentioned a second ago, you don't even have to put a person on the ladder if you, and I think there's a rule of thumb that this distance right here is supposed to be 3 times that distance. In other words, this wouldn't be safe. You should actually set that at 12 feet, or at least that this distance is triple that one. So there is some, if you're in a construction class, that's one of the things they teach is that angle. But it's like, where's the impetus for this to fall down? Why would it want to slide down the wall? Like, why did I get to there and suddenly this end went that direction? That one sliding down, and obviously because the ladder's length is constant, the bottom slid out. And once it started, it just went all the way and crashed to the ground. Where's the force? Where's the forces that are trying to do that? Because there's just 200 straight down, and therefore the floor is going to be able to push normally against it 200 straight up. But why would the wall need to push back? Why? Because that 200 is straight down. It's not pushing like in this direction. It's not pushing in that direction.
It's the weight from the base of the ladder arc line up. Difference in X value between where the weight is and where the foot is.
Yeah, it's an interesting thought, right? They are not straight above each other. Does that cause any kind of a problem? So yeah, let's play with that now. So that actually kind of turns out to be true. Again, though, I want to argue for the strength of a free body diagram. There's not a lot in this picture, but remember, the ladder is just floating in midair. I mean, that's the idea here ultimately. So if I draw the ladder sort of floating in midair, come on, straighten out for me, man. And let's call this, for no good reason, location A, and call this up here location B. And so what forces are on it? Well, we got this 200 here. Doesn't really matter if I draw it on top of the ladder or on the bottom. I got that 200 pounds. I won't bother to write it in the label. But then what other forces do you have? Well, remember, anything it's touching can only push perpendicularly, which means there would be a force here where the floor is pushing on it. Let's see, what am I going to call that? I think I'll call it force at A in the Y direction, I guess. I could have called it force of floor, force of ground, or something like that, or just force 1. And then over here is the same thing. In other words, you're going to have a force pushing on the wall. The only thing it can do is push perpendicularly back. So that'd be force at B by the language I've been using, force at B in the X direction. So, and that could be 0. That's what I was getting at earlier. It's like, there's nothing saying that's a number. It could just be 0. But then, because the ladder effectively wants to go here, in other words, that wants to go that direction and this wants to go this direction. If something is falling, you do have friction that's going to resist this. So do these two forces, or does this force at least make sense? There would actually be a resistive force of friction here. Force of friction at B, maybe I'll just call it that. Force of friction at B. There would be that in that situation. And for that reason, since this bottom point wants to move to the left, wouldn't there also be a force of friction resisting that as well? Force of friction at A. Now I actually have all the arrows in this thing. These are the potential forces. Again, there's nothing saying some of these couldn't be 0. But here's where it comes in, and it is kind of related to what Joseph's, I'm actually what a few of you said, but it really comes down to this calculation right here. If your first calculation is the sum of the moments That's kind of the surprising one. It's not just 200 down, 200 up, game over. There actually is moment calculations here. So in this picture, I'm gonna assume that this fell or whatever when this made it to 3 feet. So that's the location of the person on the ladder, is they're 3 feet over. So if that's the case, what are the forces, some of the moments around A? Well, notice these two forces down here are both aiming at A or away from A, so they're not going to cause any desire to rotate, but the other three forces are. And so wouldn't that 200-pound force multiplied by its distance directly, perpendicular from A, which is that 3 feet I mentioned a second ago, that's how far it is away from A. So that's how much desire, there is desire to rotate here. And that's what this comes down to, which I don't think is obvious in this circumstance. And that would be causing rotation in this direction, which we traditionally call negative. So there'd be that. But then isn't there also the force of B at X pushing against it as well? And since the ladder was 9 feet tall, that's how far away again that is perpendicularly from A. So the force of BX would be multiplied by 9 for its distance. But then there's also that force of B, that force of friction at B to include in this as well. So what would that be?
So when you're calculating friction, you not add, because I would be adding force of By, force of AX, but you just added friction, force of friction, X, which is not necessarily mirroring those forces, right? A force of B, there should be a force of By, right?
Not because of the wall, because the wall can't do that. Any structure that you're pushing against, like no matter what angle I push at, if I push on this desk right here, the desk can only push normal to that. It can only push perpendicular. It can't push at an angle. So that's why that's drawn in there. So there is no other forces. There's nothing else the wall can do except for push back perpendicularly. Yes, that's exactly right. And that does exactly get back to the attachment. Notice these attachments are sort of free. They're like just touching. It's not bolted. If it was bolted, then that's exactly right. There would be a force of B in the Y direction. That's exactly right. And that would have kept me from falling, I'm sure, by the way, as well. Yes, and then, yeah, you could overcome the force of the bolts if they were too weak. So then there's this force of friction. At B, and notice it's a distance of 4. Looking back up here, if this force is sitting up there pushing in that direction, isn't that a distance perpendicular the entire 4 feet? And because it's causing a rotation in this direction, we call that positive. So this would be a positive. And of course, that's the end. That's the only 3 forces that are trying to get this to rotate. And again, if this isn't going to fall, does it make sense that needs to be 0, meaning don't rotate? So we don't like this equation because it's got 2 unknowns in it. But again, this is where it kind of gets cool, because aren't these 2 equations right here, or these 2 forces, actually related to each other? The force of friction is proportional to the normal force. This is the normal force down here. This is the normal force. And so if I knew what the coefficient of friction was, I'd actually be able to kind of make a relationship between these 2. And so I haven't given that to you yet. I'm just making this up. But let's say the static coefficient of friction. And again, I don't know, I'm just making this up, but we'll say 0.2. And in our case, this is smooth concrete and aluminum. And you can probably appreciate, like, there's a lot of different kinds of finishes. On a sidewalk, they don't smooth finish it. They usually run a broom over the top of it to put a bunch of ridges. And that's exactly for friction, to keep people from biting the dust if it's a little bit wet. And so it would actually, it's not just concrete in general. It would have to be how it was finished. so forth. But this was particularly smooth. And so a number small like 0.2 kind of makes sense. And so what that would mean then is that you could actually calculate that force of friction at B by just taking the normal force, which for us is actually that force of Bx, and multiplying it by 0.2. So you're basically getting 20% of whatever the weight. And again, this is interesting because it isn't downward. We're usually used to thinking like a box on a table and I can't get it to push. So I could actually replace that force of friction at B. That's what's kind of cool. You can actually replace this with 0.2 times the force of Bx, in which case now I don't have two unknowns. And so I didn't like this equation before because it had two unknowns in it, but now it doesn't. So punch a few buttons. What does that mean, that force? So in order to keep this from rotating, basically there is a horizontal force, like the wall is required to do the job. Sorry?
28.
Did you get 28?
Oh, no, I just did the 0.2 times 4.
Got it, 0.2 times 4, so that'd be 0.8. So let's see, 600 divided by. I got 61. Did you get 61.2? So. So let's stare at that for a second. So again, that's just kind of interesting because you climb on the wall and you think my force is going straight down. So there shouldn't be any kind of forces in Y at all. They should all just be forces in X. And as long as I said, the ground can push up at 200, it's like, why would there be any desire for this to rotate? Well, when you do the sum of the moments around A, like they're actually, that wall's got to do a job. That wall's actually pushing back at 61 pounds. We'll notice all of a sudden there is a horizontal force as a result of moment. And what Joseph said is exactly true. The fact that those 200s were not straight above each other. I mean, it's kind of like if I walk up to this thing sitting on the table and I push directly across from each other, nothing happens. But if I push like this, then it does want to rotate. And that's kind of exactly what's happening there. So this does want to rotate as a result. And of course, rotation equals fall. So the question is, am I going to fall? Like, is that going to slide? Like that basically said, as long as the wall can push back at 62 pounds, and so here's this thing leaning against it, as long as the wall is like strong enough to not, be able to push back at 61 pounds, which it sort of feels like it would be. That's not very much weight. I'm leaning against the wall. And so it's like, great, no rotation, right? So it's like, where's the desire to rotate here? We just made it equal to 0, right? We made rotational equilibrium. As long as the wall can do that job, we're good. But now consider the sum of the forces in X. Like, okay, so basically what we're saying is this force of Bx up here is like 61.2 pounds. Well, now does it make sense? That would indicate that the entire ladder just wants to like move horizontally. Like how can the sum of the forces in X be 0 then and it not move if we got 62 pounds up there trying to push it to the left? Well, perhaps you see that's where this gets involved. So here's what's kind of weird. And actually, I'm not sure I even know the answer to this question. If you stop to figure out the sum of the forces in Y, and you say, okay, well, I got 200 going down, and I got force of AY going up. The question is, should I be including force of friction at B in that? Should that be included in that?
I was thinking about that. I was like, in what world does the top slide and the bottom not?
Can't if the ladder is not gonna, if the ladder stays the same length, they both move simultaneously.
I was trying to think in terms of like a 3-body diagram, but it's hard, like in the real world, and like the A will move and B will never go first.
Yeah. One of the things that's really hard about this is, again, it's a question of capacity. Like this table is sitting there, and we've talked about this in class, but this table is sitting there not working very hard right now. But it is holding up this, and this is actually made out of MDF, medium density fiberboard. It's pretty heavy, but it's sitting there and it has the capacity to it, but right now, it isn't having to work that hard until somebody comes over and sits on it. As I've said before, if you think of the table as being personified, the table was just kind of hanging out, not lifting that much weight, and so it's like 200 pounders sits on it, and it's like, oh, now it's groaning, if you will. If you personify it, it's not groaning. So the point is like, what's happening right now? Well, maybe it's pushing up 10 pounds right now. So it's sitting there with a force of 10 pounds. Well, now it's pushing 210 pounds. And so it's like, it's capacity. It's not like, you can't say that thing is pushing, it's capable of pushing 210 pounds before it breaks. Therefore, there's an arrow under it for 210 pounds, therefore it flies up to the ceiling. You see what I'm saying? It's more like a capacity. Right now, it's being asked to lift 10 pounds and it can do it. And now all of a sudden it's being asked to lift 200 pounds, 10 pounds, and it can do that. But we could put 500 pounds on it, and then suddenly it can't do that and crashes down. And that's what's kind of hard about this. I would say that force of friction at B does belong there. In other words, the wall is pushing 61 pounds right now. Therefore, that force of friction is in play. And so the 200 wants to go down, but I would say that both of these, like this is actually resisting it. It's making it so that that force of A does not have to lift the entire 200 pounds because, if you will, the ladder is dragging against the wall. So my 200 pounds is dragging against the wall. And so that's kind of helping lift, if you will. It's kind of like me sitting on the table. I am putting weight on the ladder. It is pushing against the wall. So right now friction is doing a job. So I think it does belong there. But part of the reason I say I'm not super comfortable with this is both conceptually just my own self, but I also went in and talked to Dusty, who has a master's in physics, and like this was stumping him. You know, even though this is a classic, simplest example, I mean, this is not conceptually easy. And he pointed out, which I thought was kind of cool, that it stumped Newton too, like this friction bothered Newton, who's smarter than us. So
I feel like the friction in B might just come into play when you're falling. So like if A gets out, like if you're on a wall of ice, you're just gonna eat crap like
Because
really
both
hard.
directions would be
uh-huh.
rectangle. So you're sliding, the ladder sliding down into.
Right, but if you're stationary, if A is doing its job, there's no friction at B. But the second A starts sliding, it
Well,
creates that friction. So if you're like
wouldn't
against a
it
really
be-
like concrete wall, that's
But
really
isn't that friction holding the ladder up as well?
think about it, like it doesn't matter. I mean, maybe side to side, we're in a 2-dimensional world right now.
How is the friction of B up and down?
Yeah, how is it doing? Think about life.
When you're leaning against it,
Yep.
that's the other makes contact, it's very friction there.
But if A holds, why is there friction there?
They're both holding it simultaneously.
So they are going to go simultaneously. And if the bottom had a rubber foot on it, then it would be doing a lot of the work from keeping this thing to slide out. And if the top did not have a rubber foot, then it wouldn't be able to do as much work. And so again, what makes this confusing, and I'm bringing this up just because it's a cool problem, but also just really to make you think. I'm not going to ask you a confusing question of this nature on the test. But again, it's capacity. Really, those two green forces of friction right there are capacities waiting to be accessed, if you will. So I think it is being accessed, like it belongs there. But I'd bet a lot of money on it, but I wouldn't bet like my life. So I don't feel perfect about this. And as I mentioned, you know, Dusty doesn't either. So I think it belongs because as a capacity, as I said, you put this weight on it, and now this literally is, this force right here literally is holding 61 pounds, and therefore that is causing there to be a force of friction at B, and so it's working right now. It seems like it is working, like it's doing that job, or At least it's capable of doing it. What bothers me is it isn't moving, therefore is it like not, doesn't belong? Anyway, let's pretend that it does. So if I took this 61.2 and multiplied it by 0.2 to see how much that actually is, I get about 12.2 for that. Notice that's not a lot of weight. I mean, if you're talking about 200 pounds, 12 pounds is not very much of it. So basically I can figure out then what that floor is responsible for now. And so the floor, if I'm right that that's included, what is that? 187.8. So that's what the floor is required to do. And we actually don't need to know that because in a sense, it's like, yeah, the floor is made out of concrete, like it's not going to sink into the floor. So in a sense, I find myself thinking, I don't care what that number is. It's like, I never was thinking I was going to sink the ladder through the concrete, but why do I want that number? Why is that number really important? Exactly. Now I can find the friction force down there at A because I now know the normal force.
Same where it's at. Of course, the friction BX is
Pull your mask down and say it again. I'm not hearing you.
shouldn't force of friction A be equal to force of BX.
Yeah, and that's what's interesting. So that's the conundrum right here. So let's figure this out and then let's talk about that. So, you know, we said this was the classic calculation. So since this is 187.8, and if this is still, you know, concrete wall to ladder, then this is still the same force of friction. Could there be a different one? Like if the wall's made of sheetrock and the floors, you know, it's like those could be two different numbers for sure.
Like you said, the ladder has no rubber on top, so they should have different coefficient.
Exactly, yeah. If it was the same flooring except for the bottom was rubber, then that would utterly change things. And so that's exactly right. 37.56. Call it 37.6. And so that's an important calculation. So what does that mean? Well, yeah, to stay static in the X direction, don't we just have these two forces? We have that wanting to go left and we have this wanting to go right. So wouldn't those have to be, well, I guess, equal to each other for this to be static? So the interesting thing is that you can't just add those up and set them equal to 0. Again, what we're looking for is capacity here. Like this is the calculation, this calculation we just made. What is that? That is the capacity of the floor to resist sliding. In other words, if you go over that, it's going to slide. Did we go over that? We did. 62 pounds or 61 pounds up there, and that's why I fell. Because it was wanting to slide the ladder to the left 61 pounds. The floor did not have the frictional resistance to handle that. And interestingly, and I'll kind of leave you for this for extra credit. But as I said before, I'll just write it like this. Extra credit. Find the location where force of friction at A is actually equal to that force of BX. What's interesting is to kind of rerun this calculation, except for where this distance right here isn't 3. Because as I said, what fascinated me was I got on the ladder on the first rung and it was fine. Climbed to the second one, fine. Third, fine. Got to the fourth, crash. And so if you rerun this calculation at a different distance right here, different than 3 feet, like you recalculate that at 1 and recalculate it at 2, you get completely different answers for this. My guess is, and I kind of just made this one up, but if you recalculated this whole thing with that at 1 foot, I think instead of the force up here of 61.2 being bigger than the frictional force, you'll probably get it the reverse. In other words, the frictional force will be the larger of the two numbers. Again, that's a capacity. And so since, this number up here, if it was less, then it's basically not, it can handle it. So for extra credit, can you find the kind of the exact location where it's like the balancing point, like where it's right on the edge? So play around with that if you find that interesting.
Are you recording this right
Yes. Yeah, so yeah, it's kind of fun to think that, the only things you have control over here is where is the 200 pounds. And then you could mess with the friction coefficients by, changing the way the ladder works and so forth. But it's just kind of interesting to play around with this. And you're exactly right that if you put this in Desmos and you let one variable change, that's kind of cool. My advice, just to keep it simple, would be to rerun the calculation when that distance is not 3 feet but 1 foot, rerun it at 2, and just kind of see what's going on. My guess is it won't want to slide at 1, and then I don't know, does it want to slide at 2? It's pretty far apart right now, 61 pounds and 37 pounds. Maybe it still wants to slide at 2 feet. And then maybe after, two more tries at this, 2 more scenarios where you rerun this exact same calculation, then you say, all right, now I'm going to let this distance right here not be 3, but I'm going to let it be D, like a variable, and try to solve for when these two forces are equal, 61 pounds and 37 pounds, like make them equal and figure out what that distance is. And so would be, of course, what's cool about that is you're going to be fine up to that distance, but you go above that, adios, you're going to bite the dust. Isn't that weird how, I don't know, interesting / complicated that is?
Yeah.
Something so simple.
I feel like I'm ready to fight to the death on the friction of the aspect, but
Yeah, and I really would, both for the extra credit points. And I would even encourage you to kind of, I don't know, YouTube this a little bit maybe. And I'll post what I wrote here too, along with the first part of this lecture, so you can kind of stare at it again, because again, I'm not 100% sure that this force of friction here, like that, even deserved to be a part of that moment calculation. I think it does. Dusty thought it did, but both of us we're not sure. We're not ready to bet. What's that?
How else would you find the force on DX?
Well, I'm just saying this entire friction is gone. Like all you have is these two components to it, and it's equal to 0, and you're done. But I think this is correct. All right, so you can play with that. Now, let's play with something physical, practical, tangible. Let's see, is there any point in recording anymore?